Okay, good. Okay, thank you. Okay. Now we're gonna start about diffusional separation. What is diffusional separation? In Indonesia we call it pemisahan difusional. So that means that if we will separate in molecular because of diffusion, because of diffusion. Okay, so the idea of separation processes is basically we want to if we have a mixture of A and B as the feed, if you and we want to separate it, what you're gonna get is first is the product one, which may be rich in A, and with a little bit of impurity, where the impurity is the B. So in ideal cases, it won't be possible if we get A and B, you just separate it like that, because we're talking about fluids, we're talking about particles, we're talking about a gas, for example. So based on the thermodynamics properties, you can't really separate what did 100%, but you will still have just a little bit, just a little bit of impurities here. The bottom product will, of course, gonna reach in B, but still have a little bit of impurities of A. Okay, so thinking about chemical plants, chemical industry, let's say I want to have ethanol 99.95%, so from the mixture of air, for example. So we have to separate it using separation processes. Okay, so the object of separation is a mixture. There are two types of mixture. The first one is heterogeneous mixture. If you imagine you have a cup of salt and you mix it with a cup of sand, and then you just mix it with your hand, and you're gonna see there's still you can still see the sand particles and also the salt particles. If you need to separate it again, there would be some process to separate it. For example, we call it using physical process separation. Maybe using crushing or screening, pengayakan, yeah. So, or maybe using density, maybe using dissolving one each other. So maybe we just put into the water, and then the salt will dissolve while the sand won't dissolve. So we can separate it, and then we just evaporate the salt back. So we got the salt. So, and the second one is homogeneous mixture. So this is, for example, we have air, and we really can't do things like physical process separation for a homogeneous mixture. Of course, what we need to do is we need to do the diffusional process. For example, if you want to make nitrogen, if you want to produce nitrogen, nitrogen is used for utility system or for purging. To get nitrogen from air, we usually in the chemical plant we need to install ASU or air separation unit. There are many technologies of ASU. So for example, distillation also, but we use cryogenic distillation to separate oxygen and nitrogen, or using like Professor Wenton using membrane. This is also one of the separation technologies. Okay, so the use of diffusion, we're gonna use a phase equilibrium. So we're gonna use also the use of diffusion is for phase equilibrium, and the second one is to, for example, the differences in diffusion rate. If we have two compound and one compound has more higher diffusion rate, so one, for example, this compound will have more faster rate. So what you get, you end up with more rich A in rather than B. Okay. So so to get diffusion, what do you get with diffusion in phase equilibrium? If you have a homogeneous mixture, let's say you have that example, nitrogen and oxygen. This is a homogeneous mixture. To separate it, diffusion in phase equilibrium, what you need to do is you add separating agent. The separating agent, it can be energy in form of heat, or it can be in mass. Okay, for this case, we add energy, we add heat, or maybe we remove the heat. Yeah, we cool it down. Yeah, to some temperature. And what happens is it will enter. Oops, sorry. It will enter a two phase. That area. So this homogeneous mixture, the homogeneous mixture will separate it into a two-phase compound, phase alpha and phase beta. Okay, let's say in phase alpha it is rich in A, and phase beta would be rich in B. So in the end you end up with two phase alpha and phase beta, and then these two phase can be separated. Okay, so another, for example, this is just a name, alpha and beta, for example, vapor phase and liquid phase. So both of phase has different phase, so we can separate the vapor and the liquid. Okay, up to here, there is any questions? Please talk to me. Yeah? Don't write in chat because I can hear you. I can't see you.
Not yet, ma'am.
No? Okay. Yeah, it should be okay. Is it clear enough?
Yes.
Yes, ma'am.
Yes.
Yeah.
Okay then. Okay, good. So I'm gonna continue then. Okay, now let's talk about vapor liquid equilibrium. Yeah, this is actually what I'm talking about in the previous one. If we have a mixture of A and B, for example, we have LPG, yeah, we have a mixture of propane and butane, because there are, for example, there is two compound, and there would be a volatility difference between those compounds, between A and B. Usually, how we're gonna write the name, A is actually more volatile, B is the less volatile. Later on, if we have 5 compounds, for example, the first compound is the most volatile one, and the last compound, maybe compound number 5, for example, is the least volatile. Yeah, and we add separating agent in the term of, for example, this is in the liquid phase. Yeah, for example. Okay, and we add separating agent as heat. We heat it up, this mixture, for some time, up to a temperature where there would be a mixture of vapor and liquid. So in the end, you have a vapor phase, where the vapor phase is rich in A, and the which one? This one is, yeah, and there's also a liquid, and the liquid is B, rich in B. Okay. Okay, so this is how separation processes, and this process is applied in the distillation process. Okay, now the question, ma'am, how if we want to have a really purity product? So that means this vapor, because it still has a little bit of low B, what we need to do is we do another distillation process. And again, so we will have a multi-stage distillation. So that's what we're gonna talk next week about multi-stage distillation, but the base is actually from here. So we do multi-stage distillation, distilasi bertingkat, in order to get the very pure of A. Usually the product that we want is actually in the least volatile, which is A. A is usually the product we want. Like, for example, if we start a mixture of A and B, requirement of the chemical plant, of course, okay, I want to have 100 ton per day of 100 ton per day of, for example, ethanol 99.99, yeah, for example. Okay, so what you require is actually the product. You don't really specify the bottom product, because for the bottom product later on you can be recycled, can be mixed with other feedstock. But the required is usually the product is in the least volatile, or in this A. Okay, so this is the principles of distillation process. Okay, okay, so just to summarize, the distillation process is based on vapor liquid equilibrium. Okay, now how about absorption? In absorption, the principles is gas liquid equilibrium. What does it mean? What is the difference between gas and vapor? Anyone want to try?
I'm sorry, ma'am. Can you repeat, ma'am, please?
Okay. Oh yeah. What is the difference between the gas phase and a vapor phase?
I think that vapor phase has a water content in it, while the gas is just pure of the material.
Slightly correct. What's your name?
Abdur Fauzan.
Fauzan. Okay. Yeah, slightly correct, Fauzan. How about others? What is the difference between gas and vapor? No idea. Okay. Go back to the slide. Yeah. Who want to try to answer?
Ma'am, I think in room condition, gas phase is gas, while vapor is either liquid or solid.
In the room temperature. Yes, slightly correct. I think it's better if I explain to you with this diagram, yeah, phase diagram. So this is a phase diagram of a unary or one compound. Yeah, this is P, and this is temperature, and this one should be in solid, yeah, solid. Yeah, let's say S. This is liquid, and this is vapor, and this is critical points. Yeah, critical point, and this is actually the gas. Okay, Yeah, so the gas is actually the phase where it is the condition is higher than the critical point. Okay, while the vapor is below the critical point. So what, for example, in the, let's see the color. For example, for the distillation, we're gonna talk about equilibrium between vapor and liquid. While this is for the gas, or absorption would be between gas and the absorbing liquid. Okay. Yeah. So okay. Let's say okay. So that is the difference between gas and vapor. So now for gas absorption process, we're gonna talk about gas liquid equilibrium. If we have a mixture of gas in a mixture of gas S in G, usually gas S is much lower. We call it S is solute, and G is the inert gas. For example, in the introductory video, there is CO2 in natural gas. Yeah. Okay. And now we want to remove CO2 in the natural gas. So we need to add a separating agent. In this case, is the absorbing liquid. The absorbing liquid usually can be solution, or liquid, for example, MDEA, monodiethylamine, yeah, monodiethylamine, and this particular liquid each have a really high affinity to CO2, yeah. This absorbing liquid really love gas, the CO2 gas, but natural gas doesn't dissolve into the absorbing liquid. Okay, so there are solubility difference between S to the absorbing liquid and also G to the absorbing liquid. So S can be absorbed with the absorbing liquid, but G won't be just stay in the gas phase. Okay, so the important part in the gas absorption process is the contact, yeah, the contact between the gas and the liquid. This is gonna be the basis how we design the gas absorption process. For example, we use packing. A packing is looks like apa ya? If you know macaroni or something like that, yeah, that is a typical packing, yeah. So this is the packing, and we put liquid over there. So this gonna just flow through a wetted film, yeah, like you learn in peristiwa perpindahan. The liquid would be wetted like this, while the gas phase in this direction. So there would be a contact between the gas and the liquid. Okay, so once it have a contact and there would be a mass transfer in it, and then it's gonna go into equilibrium. And with equilibrium, what happen is the solute from the gas phase will be soluble into the to the liquid phase. Yeah, so you end up with a clean gas, yeah, which is low S. So this is gas G, and you end up with the MDEA, for example, the monodiethylamine with rich in CO2. Yeah, this is the principles of gas absorption process. So later on in the course, we're gonna learn the principle of this and how to calculate this mass transfer and how to calculate the height of the packing tower, and also how what is the further process of this one, because we need to regenerate it, yeah, because we use solvent and now the solvent used, so now later we have to recycle the solvent back, so later on the solvent or the absorbing liquid can be recycled back into the mixture of gas. All right, so that is the gas liquid equilibrium. Now, for the last part or the third part is the liquid-liquid equilibrium or extraction. Yeah, uh, I would imagine extraction is as simple as if you want to make tea. Yeah, if you want to make tea, you need to stir it. You just leave the tea bag in the cup. But for tea is not liquid extraction. Tea is leaching. Yeah, solid liquid extraction is called leaching. Yeah. This one is this is liquid-liquid equilibrium. So where S is S compound, we have a S compound dissolved in the liquid L, and S is likely more dissolved. Likely more dissolved to P, and L is immiscible to liquid P. Okay. I'm sorry. In my house, there is. I think I will move to other place then. So, yeah. Okay. I will move to other place. So, okay. Yeah, this one is better. Okay. So, so S is dissolved. So what happened is, still there's. Okay, I'm sorry. I need to move to other room then.
It's okay, ma'am.
Yeah. Okay. Yeah. Oops. Okay. Yeah. Click this in there. So, yeah. For some reason why I can't. Okay. Let's see if I still can use. Yeah. Okay. So this is called extraction. Liquid equilibrium. So we have S compound dissolved in liquid L, and usually so the S compound that first dissolved in liquid L will dissolve into liquid P. So in the end, we will have two separated liquid. The liquid L, the first the origin of the material, we call it the sisa, yeah. It's called raffinate. We call it raffinate. While the P has extracted the compound S, it is called extract. Okay, so this is called liquid extraction process. Okay, so based on those three three explanation about distillation, absorption, as well as extraction. We know that phase equilibrium is it is a natural process. Yeah, it is a natural process, and it is actually a function of pressure and temperature. Okay, so based for some compound, that common compound like from hydrocarbon or common chemicals, we do have a lot of extensive thermodynamic database. You can see it at the back of your Jan Koplis book or Paris Chemical Engineering book, or and even in HICE. So based that all of them is based on the experiments, and but it also can be predicted from thermodynamical properties, and what we're gonna learn in HICE. Okay, the factors that affects equilibrium composition is the equilibrium conditions and the process configurations. Okay, so some of the use of difference of diffusion rate, for example, is this is in membrane. What you have in membrane is, for example, there is a mixture of 50% A and 50% of B. Because of there is the difference in the permeability. Yeah, okay, because of the permeability, A is more permeable to the separating medium, which is the membrane. So A is going to be richer in this other side compared to B. So the concentration of A would be higher than concentration of B. Oops. Okay, and back here. Can you still hear my voice?
Yes, ma'am.
Yes,
Yes,
ma'am.
Yes, ma'am.
Can you hear my voice?
Yes, ma'am.
Yes,
ma'am. Yes, ma'am.
Hello, hello. Are you there?
Yes, ma'am, we
Yes,
can
ma'am.
hear you.
We can hear you, ma'am.
We can hear you, ma'am.
yes, ma'am. We're here, ma'am.
Hello, are you there? Or
Yes.
Hello, ma'am. We're here.
Hello, ma'am.
Yes, ma'am. I think you can't hear us.
okay, yeah. I think my Wi-Fi is not stable, so I'm wait a minute. I'm gonna change it into phone, yeah. Into tethering.
Okay, ma'am.
Okay. Okay, okay. I hope you can hear my voice. I have changed the my internet as well, so hopefully that would be better. Okay, so now the use of difference, this is about some of the application of the use of difference in diffusion rate, where concentration A at the other side would be higher than B because of the A is have more permeability compared to B. Okay, for membrane, the differences of diffusion rate based on the separating medium, for example, based on the polymer material, and also driving force, gradient, pressure gradient, and etc. Yes, so the dividing factor is the separating medium and process configuration. Okay, so the topic of separation process would be about distillation process, about 5 weeks or so, and then absorption process about 5 weeks or so, and also liquid extraction, and also some additional process, but it is not assessed. It's using membrane. Okay, so this is my first presentation, and let's see to the next session. Okay, so now let's see to the next session. Okay, there's still, okay, this one, yeah. Okay, so I'm gonna save it. Now let's see the session, the third segment.
Ma'am?
Yeah.
I'm sorry, can I ask about the previous slide?
Yes, you can.
I'm still confused about the difference of driving factor and defining factor. What is the difference?
Driving factor
And defining factor.
Oh, in the previous one, yeah. Okay.
The very last one.
Okay, the last presentation. Oh, this one. Okay. The driving forces is this will influence the rate. Driving force will influence the rate. For example, if you have higher concentration gradient, then the rate would be higher as well. If you have higher pressure gradient, the rate for diffusion would be higher as well. But the defining factor would be looks like the media, the separating medium. If you use different membrane, for example, it will have different performance. If you have a configuration, if you have series, if you have parallel, for example, this is more about the method or the configuration or the media. But this driving force is more about going inside the formula later on. Is it help?
Yeah, thank you, ma'am.
Okay, good.
Ma'am, I'm sorry, but I cannot find these slides in the files.
This one?
Yes, only the video, but there's no the PPT file.
No PPT yet? Let's check it. Should be in general. Let's see. In the file, class materials. Please open the general one, the general one, class material internationals, module 1, introduction, and this one. On number 2,
Yes, ma'am.
Okay. Only number 2. Okay then. Yeah. Okay. Good. Thank you. Now let's open. This is. I will close it. Now I'm gonna start explaining about this one. Yeah. Yeah. Okay. Now we go to the third session, the third video about a vapor equilibrium binary mixture. Okay. Now this one. This is the. Oh, sorry. I should put the gas over here. Yeah. It's not that in that area. This area. Yeah. Mm. Sorry, it should be a little bit of freeze in here. Yeah, I need to point that the gas is not in this area. This is actually supercritical fluid, but the gas is in this area. So the gas is the difference of gas and vapor is if the gas is at higher than critical points at a pressure.
I'm sorry, but what we see here is the presenter view, like not the slides, not
Oh,
the full
really?
slides.
Okay.
Yes.
Yeah. Discharge. Presenter view. Okay. Can you see it now?
Still in the presenter view, ma'am.
Okay, how should I do? Slideshow, custom show, presenter view. Still in presenter view, yeah?
Yes, still, ma'am.
How about this one?
Now it's fixed. Yeah.
Okay, good. Okay. Yeah, so this is a vapor liquid equilibrium. So yeah, this one there. For the gas, yeah, the gas is around this area, and this is vapor. So in what we're gonna look at is this area. The shaded area is the liquid gas vapor. The liquid gas vapor or the liquid and vapor area is between triple points and critical points. Yeah. Okay. Now, from this area, from this figure, this the vapor liquid equilibrium, I'm gonna take this line and then put it into another diagram. Okay. So from the P and the T, there is some sort of this line, this curve. This is the liquid phase, and this is the vapor phase for a compound. Let's say a compound A, and I'm gonna move it into another slide. Yeah. So this is compound A. If we have compound B, maybe something like this. This has low compound volatility at certain temperature, at certain pressure. Yeah, a similar pressure, and we combine them together. What happened? It would be looks like this. Yeah. Okay. Let the animation goes. Okay. Yeah. So if you have two different vapor-liquid equilibrium diagram, compound A and also compound B. The A is the red one, the B is the blue one, and then you combine it, it would be looks like this. Okay, so from here you can see that TA is it lower or higher than B?
Lower, ma'am.
Lower, yeah. The boiling point of this is boiling point, yeah. The boiling point of A is higher than boiling point B. So at this condition, for example, in this condition, or maybe in this condition, B is in the liquid. B is in the liquid phase, while A is in the vapor phase, which is A is more volatile compared to B, right? Okay, up to here?
Yes, ma'am.
Okay, now this is if we have one compound and one compound. Now what happens if we combine them together? If we combine them together, it actually, it won't be look like this, but it gonna be, okay, it's actually gonna be looks like the green curve here. What happened is there would be an area of this green one is for the mixture. So this is the area where so that means if you combine A and B together, you end up would be at point P. In here, for example, this is all liquid, and when you go to you will go to this area here where this area is a two-phase region, vapor phase and also the liquid phase. And up to here, this another line of the green line, and then it's gonna be full liquid. Okay, can you get it? So usually in for one compound, you straightforward get from, okay, this is liquid, and this is and this is vapor, yeah. But for here, there would be an area just a little bit here between the two green lines is the area where it has a two-phase compound, two-phase area. And this dot line here, the green one, is called the critical points of mixture. Okay. Yeah. Any question up to here? Any question? No? Okay, I'm gonna continue. Okay. Yeah. So if you have a binary mixture instead of, so let's say we call it A and B, yeah. So 100% A is the red line. This would be the curve where yeah, the boundary between a liquid and vapor. Okay, if you have 100% B, or I can say this is 0% A. Yeah, I will put it in A. It will have these blue lines, and these blue lines is the boundary between liquid and the vapor. Okay, what happens if you have a mixture of 50% A, which is the remaining is 50% B? You end up with with an area, yeah, with an area between these green lines. What happened if 25% A? Can you imagine? Can you guess?
Maybe it will be closer to the right side, ma'am.
Yeah, 25% A. Oh yeah, 25% A would be go to the right side here, yeah. And there would be still two lines as well. There would be area, but the area it would be much apa ya, lebih tipis, it's more a thin area. So it would be looks like this. Yeah. So if you have so that means we have pressure. Yeah, we have temperature. Now, if we make a few diagrams, for example, 100% A, 0% A, 50% A, or maybe somewhere in between here, you end up with this area, yeah, vapor, liquid, uap, cair. Okay, or and yeah. So so you can try, or you can try to imagine if you have the 3D between mole fraction, temperature and pressure, it would be looks like this tongue, yeah, kayak lidah ya, looks like a tongue. So in the middle here there would be an area, and there would be like some sort of a thick layer. At the end of here would be just a line. At the end of here would be just line, and up to here would be a little bit of mengerucut ya. Would be just going to this area. Okay, so this is the P, we call it PT, pressure, temperature, XY. What is XY? Is the mole fraction. Yeah, we will say X is for the mole fraction of the liquid phase. Of the liquid phase. Y is the mole fraction of the vapor phase, not the gas phase, yeah, but the vapor phase. Okay, so this is the mole fraction, and this one is the liquid one. So yeah, we can yeah, it can be schematic like this, but I'm gonna show you in the next slides, in the next segment about how to, yeah, about the real diagram, but it would be looks like this. So that would be looks like the 3D area like a tongue, yeah, seperti lidah, and the area is the size is the vapor liquid equilibrium. Why this is important? Because we do want to have a vapor liquid region, then we can separate the liquid phase and the vapor phase for the purpose of separation processes. Okay. So, okay. Up to here, any questions?
Clear, ma'am.
Not yet, ma'am.
Okay, so think about imagining it in 3D, combine them together so it would look like a tongue, yeah, I would say. Now, usually for condition, usually we need to specify the condition. Sometimes it would be in constant pressure, sometimes it should be in a constant temperature, yeah. So let's see this this diagram. In this diagram, we have if we have this plane here, yeah, I have something to cut horizontally with these brown lines. This is at, what do you think? Is it at a constant pressure or is it a constant temperature?
Pressure?
Yeah, right.
Constant pressure.
This is at concentration. So if you cut through this model through a constant pressure, what you get would be looks like that. Yeah. If you cut through. Okay, you end up with this one at the concentration, and then this is there is a profile of temperature here. There's a temperature on here. If you cut at a constant temperature in this green line, what you're gonna get would be maybe looks like that one. Okay. So if you slice it, would be looks like this. This is a vapor liquid equilibrium area at a constant pressure because horizontal. We cut it through horizontal, and this one we cut it through vertical at a constant temperature. Would be looks like this. So this is the area for the vapor liquid equilibrium. Okay, yeah, so then it's the end of the session 3, and we're gonna continue in the next segment. More explanation would be in the next segment. Yeah, I'm gonna close this. And let's see. Can you see the PPT?
Yes, ma'am, but in the presenter mode.
Okay. How about this one? How about this one? Good?
Yes,
ma'am. It's good.
Good,
Yeah.
ma'am.
Okay. Yeah. Now, those diagrams, this is from the Tribal book, yeah? It would be looks like this in the Tribal book, yeah? So this is, if we called it number 1 here, the number 1 here is the pure A. Yeah, this is, so this is pure A, so the, let's say X equal to 1. 4 if for liquid. This is X equal to 0 this case, yeah. So X and Y, so X is for mole fraction of A in the liquid phase, while Y is the mole fraction A in the vapor phase. Okay, so if you cut through the constant pressure, you end up with this area, yeah. So you can see that this side would be liquid, and the it would be vapor, and this side would be liquid. Yeah, because this is vapor, this area is vapor, and this is liquid. If you cut through at a constant temperature, the up there would be liquid, and the down here would be vapor. But for the purpose of distillation, what do you think is easier, to change the temperature or to change the pressure?
Change the temperature, miss?
Yeah, that's right. So you can change the temperature by adding heat or by providing energy, or just put some condenser to remove the heat, and then you can lower the temperature. Yeah, but it is much difficult to change the pressure. So because of that purposes, what we're gonna discuss the next slide would be more about at the changing temperature or a constant pressure. Okay, it should be noted that this tongue diagram here, it would looks like a tongue, and then it's gonna end up at one point. So the area up to here is much smaller. Yeah. Okay. So yeah, so this is like I said before, if you cut through the temperature, but we won't use this diagram because it is yeah, more difficult to change the pressure compared to change temperature. And this is at at a constant temperature. At a constant temperature, you end up the top one would be a liquid phase, the lower one would be a vapor, and there is a bubble point, yeah, bubble point pressure, where the liquid start to have a vapor. So I would imagine a bubble point or a bubble point temperature, a bubble point pressure is where you have uh, a, yeah, a cup or a container of liquid, and it starts having bubble. Have a stream of vapor and it start to have a dew, mulai mengembun, yeah, it have a liquid phase in it, so that it is called a dew point, this one here, yeah. So what happened here, so this is the mole fraction of A, this is 0% of A or 100% B, that we call write B here, and this is A or 100% or 1 mole fraction A is 1. So if we start from, let's say, R, what is the condition for R? The phase of R?
Vapor.
Vapor, right. This is vapor, yeah. Okay, what is the condition is S?
Start forming the
Start forming
bubble.
liquid, or it is called saturated vapor. Yeah. What happened in here?
Starts forming bubble. Wait, what?
This is a two-phase region. Yeah. In here there would be a two-phase region, which is liquid and vapor. What is the composition of the liquid? This one. And then you read it to here. Okay? So, yeah, because the composition of liquid is this one, the T. Yeah? So, XA at T. What is the composition of the vapor? The V one.
V.
Yeah,
V.
the XA would be at the V. What is the amount, the relatively amount, the ratio between the liquid and the vapor? You can use lever rule. So if I write this is A, this is B, this is C, the ratio of let's say liquid to vapor, it would be, this is area is the liquid, so the ratio would be this one. So the length of this, yeah.
I'm sorry, but in my screen, your screen is not changing, ma'am. There are no additional writing.
In mine too.
Really?
Mine too, ma'am. Yes, ma'am.
From the beginning?
No, only the lever rule.
Yes.
Can you write? Can you see my writing now?
No.
We cannot see the lever rule one, ma'am.
Oh, okay. Why? Can you see my arrow?
We can see the arrow about to face.
Is my arrow is moving?
Oh,
Oh,
no.
now it's better, but mine right now.
But my arrow is moving, right?
Um,
Yes,
yes, it's moving.
yes,
Now we
ma'am.
can see.
Okay. Let's change color then. Okay. Can you see my my green color?
Yes, ma'am.
Yes, ma'am.
Okay. So I'm gonna go back to the inside the graph. Yeah, hopefully you can see it. So if I put it, this is A, this is point A, this is point B, this is point C. Can you see it now?
Yes.
Yes, we can.
Okay. So the ratio of liquid of the vapor, because this is liquid is over here. The ratio would be the length of BC. So the length of BC. So divided by the length of, looks like, I think I teach you bakon before, yeah? Yeah, similar to that. So, and the length of the vapor that way. Yeah, so this is, so in this point, which one is higher? Which one is the higher? Is it the liquid or the vapor?
The vapor.
Yes, you're right, because this is the vapor. No, liquid or vapor? I think should be
Oh,
liquid, yeah?
Liquid.
ma'am.
Liquid, because this is the liquid, yeah? Okay. And then go back to the U. What happened in U?
The
Only,
point.
First dew starts to form.
Yeah, it is full. It is all actually saturated liquid, or all become liquid, yeah? The composition is the liquid. Okay. Is it, do it have vapor on it?
Small percentage, maybe.
Yeah, very, very small percentage. Yeah, the percentage is in here, but it's very, very small percentage. And if it is in W, so that would be a full liquid, yeah, or undercooled liquid. Okay, that is for pressure, similar with the at different at constant pressure. Would be looks like this. So this is an ideal binary mixture phase diagram in a constant pressure. Pinnacle. Okay, similar, yeah. When you so for a constant pressure, what you have, you end up with some sort of area here. The other side, or here is the top one, is gonna be the vapor atau uap, and the lower one is the liquid. Yeah, so this side would be liquid. If I want to draw them in 3D. So this is X, Y, and this is T. Yeah, so it would look like this. A similar one, you can say it from G or vapor the same. For example, this is O vapor, and you cool it down into M. M would be, is it the dew points or bubble points?
Dew points.
dew
Dew
point.
points. Yeah, this is dew points because all vapor and it's gonna start to condense. Yeah, it start to condense. So it's called dew points. And this is the composition, composition of the dew points. It did have the liquid points, but very, very few. This is the liquid point, the mole fraction of the liquid. And to this area, again, it's gonna change into two phase. L, so this is the composition for the liquid. This is the composition of the phase, and the relatively amount is around, you can see also the left rule. And if you cool it down again, it goes into the bubble points, or it is called, is it saturated liquid or saturated vapor?
Saturated vapor. Saturated liquid.
Yeah, saturated liquid, right. Okay, and then you get this one. Okay, yeah, hopefully you should be able to read the phase, also the composition, yeah. Now, because in this one, in every point in the two-phase region, it do have the pairs between N and M, yeah. N is the is it liquid or is it a vapor?
Liquid.
Liquid. So there is a pair between Xn and Ym. Yeah, there is a pair between XL decides with the which one? YK. There's also a pair between this one, or XH with YJ, and so on. So if you want to plot this diagram, this is TXY diagram into let's say YX diagram. I can, or I think I will just erase, yeah. Okay, just because I want to read, I want to try to draw the diagram. Usually in this lecture, I use a lot of blackboard or whiteboard, because otherwise we really can't understand things in a separation process if we don't use whiteboard. Even if you have PowerPoints or PPT or Bang Soal, yeah, it would be yeah, you really can't read it if you don't know how to do it by yourself. Okay, so okay, I'm gonna start drawing. Hopefully, it should be good. This one, pen color. Okay. No. Good. Yeah. Okay. So, what happened if I want to change them into XY diagram? Let's say this is X, this is Y. The idea is to use your ruler to have X and Y together. And in all these pairs, you can read down to there, for example, let's use for example 0.5. So this is 0.4 something maybe, and this is 0.1 to 2.51. So we can put a pair. So the X here is, for example, this area, this one. Yeah, this is the X for the N, and the pair is N, M, which around this area. So I'm gonna use my hand to using yeah, to find, for maybe using by measuring the distance between 0 to M here. I'm gonna measure the same distance to here, so then I can plot. So this is gonna be 1 point for N and M. Okay, you can try. This is the X. This is the X, and this is the Y. Okay, so this is become 1 point. Let's try another one, maybe L and K. So L would be, this is the X-axis around this length. So I'm gonna put around this area, this length, and the K like more than half of it. So would be maybe half of it. maybe around this one. Okay. This one there. This is a point of a pair of x and y for points L and K. Okay, another one for H and J. So let's say this is, I put H for the X because this is X, yeah, for the liquid, and this is the vapor. J is much more go to the 0.1, so maybe around this one there. That point. And then what happened, last one maybe D, maybe at D equal to here, but F is really close to 1 for the Y. So I get these points. And I also know I have these points and these points as similar X and Y. So I'm going to put these points. So then I can draw the curve. The green one here, yeah, using that one. And this is the curve for TXY. Yeah. Okay, I'm just gonna put a picture. Yeah. So this is the green one is the curve of XY ideal binary mixture diagram at a constant pressure. So it's gonna be looks like this. Okay. Any question? You should be able to use by your ruler or using millimeter block to change the TXY into XY. Okay. Any questions up to here?
Ma'am,
Yeah.
I'm still confused. So with this XY chart, so it's possible to have both X and Y fraction is 1, or I
Yeah.
was mistaken.
Okay. So like in these points, because in this point, because it's only pure compound, right? Because in here, this point is a pure compound. So if you have a pure compound of A, if you have a liquid, what is the mole fraction of the liquid, of A in the liquid? Of course 1, because it's only one composition. And B, and how about the mole fraction in the vapor phase? Also 1, because there is no other compound in here. That's why it's called this point there.
Oh, okay. Thank you.
Yeah, this is looks like go back to the thermo, yeah. But anyway, I'm gonna still, check this one again and then try to review a little bit. Okay, so this is what looks like for the ideal binary mixture phase diagram or XY diagram at a constant pressure. So using this diagram at any point, at any point here, you can have the pair of the mole fraction in the liquid as well as the mole fraction of the vapor. So for example, in this point, what is the mole fraction of A in the liquid? You go to this one there. What is the mole fraction of A in the vapor? That one there. And then you read it. Okay? Up to here, any questions? Any more questions? No?
Ma'am, I would like to
Yeah.
ask, could you repeat how to change it from the VLE to the ideal binary mixture?
Okay. From here to here, yeah. Should I let's let's add maybe one. No, not this one. How if we add white screen maybe? Okay, yeah. Okay, okay. Ya, anggap. This is bad. Okay. And anyway, it's basically like this. You need a lot of practice. Yeah. Here, first you need to have a ruler. Yeah, you have a scale. You need to have a scale from here to here. Yeah, from 0. This is 0.5, and this is 1. Okay. So first read the pair between N and M. Okay. This is the pair of one temperature, right? This is the mole fraction of the liquid phase. This is the mole fraction of the vapor phase, right? What is the mole fraction of the liquid phase? You read to here, this one, maybe about, I don't know, 0.1 something, yeah? And then you put it in on 0.1 here, on this point. Okay? Now here is in pairs with the vapor phase. What is the vapor composition? A Y, yeah, which is Y. This is one here, and you read it here. Maybe let's say 0.4. Okay, this 0.4 is not X but Y because it is in vapor phase. For the vapor phase, the X is in here. Okay, so then you use your ruler and then find your maybe 0.4, let's say, and you put pair between the X and the Y to get this point. Okay, and you can do the same for other pairs, and then you will get those points, and then you start to sketch the curve between that one. Is it clear enough?
Yes, ma'am, I understand. Thank you.
Yeah, okay, good. Okay, this should be recorded, so you can go back and check this session if you want to, because I'm thinking to give you some exercise about how to change the pressure and how the TXY diagram to the XY diagram. Okay, now let's move to here. So we know that, so this is the TXY diagram at lower temperature, at lower pressure, lower pressure, and with the increasing pressure, the area between the vapor liquid equilibrium is getting smaller and even at the higher low temperature, and at a high temperature, at high pressure, the length for two-phase area is become smaller, this one and this one, right? So if we think about the separation processes, of course, we want to have a pure compound A for the product. In high pressure, we can't get it because the maximum is only at this composition. In this higher pressure, the maximum composition is only up to here. Right. So that's why for operational purposes and because of the thermodynamics of this one, it is not recommended to do distillation at such a high pressure like this. Okay. So this diagram tells you that if you want to do a good separation, do it where it still have those fully envelope from 0 to 1. Okay, so when we plot it into the XY diagram, at lower temperature would be looks like this, but at lower pressure would be looks like this. You can go to pure compound A, but at high pressure it's only up to like 1/3 or 1/5 2/3 of the composition, of course you don't want it. So then you have to manipulate the operating condition, lowering the condition. Even for some essential oils, the distillation is happen at vacuum. It's actually because it could have a good range separation, and also it won't damage the properties of the essential oil. This is non-ideal. So this is a typical of one non-ideal TXY diagram. So if I'm in this area, what is the maximum for me to get the product? I only can do distillation up to this one. Yeah, so this is called azeotrope. Yeah, in solid liquid we call it eutectic. In liquid vapor we call it azeotrope area. So that's why there would be a topic called distillation azeotrope, yeah, but it's not covered in this course. It is a technique how to deal with azeotrope process by adding another mixture to prevent this distillation azeotrope, because in this distillation azeotrope you really can't get into this one there, but you have to add something to the mixture. Yeah, so in distillation azeotrope, the range of separation, if you start from here, is only up to here, and if you start from here, for example, only up to here or here. So there would be two different area for doing distillation. Okay, so this is an example of a water ethanol water system. For example, pressure of 1 atm, and boiling point of ethanol is almost 80 degrees Celsius, less than 77.4, and boiling point is 100. A, or ethanol, is more volatile than B, and we can sketch them in a diagram if we know the temperature as well as the X and Y. Yeah, so in a quiz or in a problems, you will be given the data of T and X and Y, and you should be able to sketch it. Maybe you can sketch it in Excel if you want, and it would be look like this. Yeah, it would be looks like this. This is the TXY curve for ethanol. This is also azeotrope around this area, so that's why up to here, yeah, that's why the ethanol techniques, yeah, if you remember, only up to 95%, yeah, because the distillation only up to here. And this one is the XY diagram. Again, the similar method. You have a pair between liquid and vapor, liquid and vapor, liquid and vapor, liquid and vapor, liquid and vapor. Yeah, which is this data, and then you mix. You put it into the XY diagram. It's gonna be looks like this one. Okay, any questions?
Miss, I want to ask you a question.
Yeah.
Does that mean that if we increase the pressure, there will be less likely to have a two-phase diagram?
If we increase more than this one?
Yes, if we increase the pressure, there will be less.
It would be a critical points. The critical points, then there would be no separation. Yeah, this one. Yeah, there would be critical points there.
Oh, okay, Miss. Thank you.
Yeah. The lesson from this diagram, you have to have a reasonable two-phase liquid paper in order to separate those compounds.
Ma'am?
Yeah.
So I was mistaken, so the title is not supposed to be constant pressure, right, ma'am?
Yeah, it's still constant pressure, but at different pressure. Yeah,
Okay.
yeah. This is constant pressure. I mean, yeah. One of these is one condition. Is one condition. One of these is one condition. So this is vapor liquid equilibrium at P1. This is vapor liquid condition at P2. This is at P3. But those P up to that one is a higher pressure. Get it? Is it clear enough?
Oh, okay, ma'am.
Yeah. So, but the lesson from here is actually, when you have to select the temperature, is it better to select the lower one temperature? Because but you have to check the phase diagram, of course, because you need to check the TXY diagram, because if you working on the higher pressure, your area for separation only up to this composition. Okay?
Ma'am?
Yeah.
So I just want to make sure. So for distillation, it is better to do it in low pressure and low temperature.
Low pressure, but temperature will for this case, yeah.
And the temperature will follow.
Yeah. Temperature will follow. But
Okay.
later on, for practice, this is based on the TXY diagram. But of course, we're gonna see also in the fractionation column, in the distillation column later, we need to check about condenser. We need to check about reboiler later on. I'm gonna explain it to you next week.
Okay, thank you.
Yeah. Okay. Okay, so this is number 4. Okay. Maybe I'm gonna explain one more, a little bit exhausting. Okay, segment 5. Now, share desktop. Okay, can you see my slide?
Yes, ma'am.
Okay. Oh, I can use my subtitle there. Okay, then. Is it okay to use subtitle here? Okay, then. Yeah. Next. Right. Okay, let's talk about the TXY diagram analysis, about the liquid vapor again. So I should write this cair or liquid. This is vapor, uap. Okay. And you understand that, so what happened in the distillation column, you can start with a feed at F1 at temperature 1, and you heat it up to TB, right, to be a saturated liquid with the temperature of TB. Or you can start with F2 at temperature 2, and then you cool it down up to a saturated vapor and at the Joule temperature. Got it? Up to here? Right, I'm gonna continue the slide. Okay, so now if I have, if let's say I've started with feed 1 or and I heat it up to 0.3, what happened here? What happened in the 0.3?
Two-phased mixture.
Yeah, it's gonna be two-phase. Would be two-phase, a liquid phase and a vapor phase. There would be a liquid here, and there would be a vapor here. For the liquid, what is the composition of the liquid?
0.2.
Yeah, 0.2. You can read it here. Good. 0.2. And what is the composition of the vapor?
0.6.
Yeah, so you go that way, and then this point, and then go then using your ruler, and you will find the mole fraction of the vapor for A is 0.6. Okay. Now, I'm gonna cool this down. Sorry, I forgot about this one. What is the ratio of vapor to liquid? Use your
3.
eyes and use your ruler.
3.
What is the ratio for the amount of the vapor and the amount of the liquid? Using referral?
It's 50-50, ma'am.
50-50, good. Yeah. 50-50, yeah? 50-50. So it would be maybe about 1 divided by 1. Okay. Now let's see here. Let's see the point 4. Okay. Now in point 4, what is the mole fraction of A? Mole fraction of A in the liquid phase. Can you approximate? Maybe this is 0.3 around here, so maybe about 0.32, maybe?
Yes.
Yes, miss.
Okay, let's say, yeah. This is what I'm talking about. How you read the graph. Of course, we're gonna see your work, and also we're gonna check is it okay 3.2 0.32 0.33 is fine, but if you read it 0.4 it is wrong. Yeah, so don't afraid, so just read it carefully based on what you write. Okay, what is the mole fraction of the vapor? So if this is 0.8, maybe this is 0.7, maybe 0.74, let's say, yeah. Okay, what is the ratio between liquid and vapor? So this is one part, and this is, if I'm gonna say it, 1, 2, 3, 4. So I think it's about the liquid part would be 4 part, and the vapor part would be 1 part. Yeah. Okay. This is okay, guys. I need to tell you, this is an engineering way to do that. Okay. You can use your ruler to measure this length and divide it by this length. But I also can use, usually I use my finger, or use you can use pen, you can use something. But this is engineering way to measure something. Yeah, this part and compared to that part. Yeah, for example. Okay, so in this three in this point 4, you end up with more liquid or more vapor?
More liquid, ma'am.
Yeah, more liquid, good. Okay. Conversely, you also can check if you heat it up more. Here, of course, you also can do things like I did before. So for this case, the XA would be around maybe less than 0.2, maybe 0.11 maybe, or NYA also maybe from this area. This is 0.5, maybe about 0.47. What I'm doing is only approximation, but for you, please do using ruler. Okay, and you also can find the ratio of liquid to vapor. Okay, so what the implication to read this one there? Now, if I have to, now I have this two blue points there. One mount is full in a saturated vapor. Yeah, one amount, the blue one here, is in fully liquid vapor, liquid saturated liquid. So I have F1. This F1 I heat it up to here, up to bubble point temperature. So it is saturated liquid, and I have another feed F2, and I cool it down up to only TD here. Okay, and after that. It's the next session then. And I'm gonna mix them together and what happened to the diagram, okay? And it's actually gonna be explained in the next session. All right, so I'm gonna close this and continue in the next session.